Alright, this combined loading problem will look at two different links in this chain. First, we'll analyze the solid link. And then we will look at what happens with the open link right here. So we'll need some section properties to do the analysis. This is a cut view of the face. See the diameter of the actual body of the link is 1/4 of an inch, which gives us an area of 0.0491 square inches, and we have a section moment of inertia, pi over 64, d to the 4th, 191.75 times 10 to the minus 6 inches to the 4th. So looking at the solid link, if we take a section as designated at AA, we end up with a C-shaped portion. The applied force to the entire chain is 300 pounds. So we have that aligned along the center line, 300 pounds. We know that each half of the link is going to have an internal force, and by symmetry we can see that that's got to be 150 pounds in this case. It's balanced, so that has that link in equilibrium. If we have that load of 150 pounds, we then have an axial stress that's just the force over the area. And that is a little over 3,000 psi. In this case, again, it's symmetric in both sides, so the maximum is at 3060. Now, when we look at the open link, this is the free surface, and this is the surface on the bottom half where we would have the section at AA. We still have our 300-pound applied force in the vertical center that I'll indicate with a dashed line. But now this free surface cannot obviously develop a reaction force. We have our axial P, but in order to keep this in equilibrium, we're going to need a moment because of the offset between the line of action of the axial reaction at the section cut and the line of action of the applied force. Now that distance, the overall center to center of the link is 3/4 of an inch, so we know that this distance is half of that. We also know that this bending moment creates a normal stress, so we need to have a picture of the geometry of the cross section of this cut face. So taking sort of a larger view here, we have a neutral axis, and this dimension, which was the diameter of the link body, is 0.25. So our C is 0.25 over 2 inches. Okay, so that establishes the geometry of the face, the geometry of the link, and now we need to calculate what these stresses are. For the axial case, for the axial load, in this case, we only have one axial load to balance, so instead of the 150 being split between both sides of the link, we now have the internal reaction force that is 300 pounds. So the stress that results from that is 300 pounds over the cross-sectional area of 0.0491. So now this time it is twice as much, a little over 6,000 pounds. For the bending, we know that the moment, reaction moment, has to equal the force times the distance between the lines of action. So that force is 300 pounds, and that separation distance is my 0.75 divided by 2, or 375. So my reaction moment has to be 112.5 inch-pounds. Stress resulting from a bending moment, that maximum value is our MC over the moment of inertia. So we have 112.5 inch-pounds. This separation distance, C, is 0.125 inches, and the moment of inertia that we calculated up at the beginning, 171, or 191 times 10 to the minus 6, and that is 73338 psi. So a much larger, an order of magnitude larger, and so your worst case scenario is going to be the total of that. Your maximum worst case has to be the combination of the axial and the bending. So 6,000, oops, that's one too many ones. Not sure where that line came from. So 6,111 psi from the axial loading, and 73,338 from the bending load is a total of 79,449 psi. So a vastly different answer than the 3,000 psi for the overall link. So for the open link, in summary, is about 79, almost 80,000 psi. That's one too many zeros. It's about 80,000 psi, and the maximum for the closed normal link is just over 3,000. And I guess that leads into a bit of a discussion about carabiner design. So here's sort of a regular D-gate carabiner, and they offset where the rope will sit to lessen that separation distance between the load-bearing closed side and the location of the applied force.